Hello everyone, I'm Shwetha ji, a PhD research scholar from UBC College of Engineering, Bangalore, from India, and my paper title is An Improved Whale Optimization Algorithm of PI Control for Three-Phase PWM Rectifier. Coming to the content section, it includes abstract introduction to three-phase PWM rectifier, mathematical model of VSR, controller design, control strategy, whale optimization algorithm, results and discussion, conclusion, and references. Moving to the abstract part, rectifier plays a crucial role in converting AC from the grid into DC for battery charging and motor operations. The performance of rectifier is mainly influenced by the control algorithms which are employed in it. Hence, this work mainly represents the optimization of proportional integral, that is PI controller designed for rectifiers in EV applications. The proposed controller aims to achieve high efficiency, fast response, and robustness to variations in load and input voltage. The optimization process incorporated in this work is fail optimization topology for tuning the PI controller parameters. The objective is to minimize a cost function that represents the deviation of the rectifier from output from the desired characteristics under various operating conditions. The optimized PI controller contributes to maximizing energy efficiency, extending battery life, and enhancing the overall reliability of the electric vehicle propulsion system. These are the content abstract part. While coming to the introduction part, introduction to the three-phase PWM rectifier and the drawbacks of PI controller. Various rectifier types find applications in different scenarios, but three-phase full-wave rectifier circuit which are employing a PWM techniques are widely utilized in EV charging applications because they offer several advantages, including sinusoidal input current, low harmonic content, and a high power factor. While coming to the drawback of a PI controller, one of the significant drawbacks of a PI controller is integral windup. This occurs when the integral term continues to accumulate error even when the system is saturated or unable to respond due to the physical constraints or limits. When the control signal saturates, the integral term keeps integrating the error, leading to overshoot or oscillation when the system becomes active again. Hence, this phenomena can degrade the control performance, especially in systems with large set point changes. To overcome from this problem, an optimization of PI controller parameters are necessary. Hence, a novel optimized topology called whale optimization to optimize the PI controller is adopted in the three-phase PWM rectifier circuit. While coming to the mathematical model of a three-phase VSR, that is voltage source rectifier. The main circuit of the three-phase PWM rectifier circuit is depicted in figure 1, where UA, UB, UC represents the power supply voltage of each side, each phase grid side, and IA, IB, IC denotes the input current of the each phase grid side. L indicates the filter inductance, R signifies the resistance, and the C represents the DC side capacitor. UDC is the DC side output voltage. IDC is the DC side output current. RL stands for the load resistant, and the switch 1 to 6 represents the denotes the IGBT with freewheeling diodes. While coming to the equation 1, it is derived from the KCL KVL equations which are applied to the circuit. And for coming to the equation 2, which represent the characteristics of a three-phase power supply. This is the mathematical model of a three-phase PWM rectifier in a three-phase coordinate stationary coordinate system. Hence, it includes 4 equations, making it complex to design a control system. Hence, there is a mathematical simplification is further needed for it. Hence, the transformation of the ABC three-phase stationary coordinate system is introduced to the DQ coordinate rotating coordinate system. The control of a PWM rectifier becomes complex due to the time varying nature of a variables on the AC side. Hence, the proposed solution involving coordinating a transformation into a synchronous rotation coordinate system, that is DQ, to the streamline control demands are executed here. While coming to the controller design part, with UD, UQ as output and ID, IQ as input, the PI controller is used for control. Hence, considering the need for feed-forwarding decoupling, it can be derived so that which is shown in equation 3, where Kp and Ki represents the coefficients of proportional and integration for the PI controller, which are respectively given in the circuit. From the following equation, that is 3, the present configuration shows a closed loop involving the current ID and IQ within the system. However, the control system currently lacks interaction with the output voltage on the DC side. The primary control loop, known as the voltage closed loop, holds the current closed loop, making it the outermost closed loop. It is referred to the outer voltage loop, while the inner control mechanism, which regulates the current, is termed in the inner current loop. While coming to the equation 4 and 5, the voltage closed loop control system can be described in following, that is equation 4, where UDC is the reference voltage in this control scheme. The error signal is fed into the PI controller, which calculates the control signal ID to adjust the voltage on the DC side. The proportional term adjusts the output based on the current error, while the integral term helps eliminate any steady state error. The output of the PI controller ID is then used to regulate the current in the DC axis of the system, allowing for adjustments to the voltage on the DC side. Hence, this closed loop control system enables the control system to interact with the DC side voltage fluctuations and regulate them according to the reference voltage VDC. Hence, the current controller can be derived in equation 5, that is ID. And while coming to the control strategy, the figure 3 illustrates a complete system diagram of the three-phase PWM rectifier. The outer voltage loop serves to stabilize the DC side voltage of the rectifier, ensuring it should remain in constant. To maintain unity power factor operation, the reactive current IQ is set to 0. The active current ID and reactive current IQ are individually compared with feedback values corresponding to the current component on the DQ axis. The output undergoes vector transformation and is then regulated by a space vector modulator to control the switching states within the rectifier. As a result of this process, the AC side current waveform of the rectifier becomes sinusoidal and to achieve the unity power factor. This control strategy offers numerous benefits, including rapid dynamic response, excellent steady state performance, and inherent current limiting protection. It effectively eliminates the current steady state error and maintains the unity power factor. A novel stepped voltage setting strategy has been developed in this study to enhance the control effectiveness. While coming to the whale optimization algorithm for PI tuning, the concept of WOA originates from the bubble net attacking strategy, where whales, coral fish is creating spiral-shaped air pockets around them up to 12 meters below the water surface, then ascending to trap and capture their targeted prey. In terms of whale observations, the methodological approach is reflected in this algorithm throughout the complex search for food, which can be significantly interpreted by the old patterns rather than the arbitrary selecting alternative courses of action. The behavior of humpback whales surrounding prey and updating their situation to optimize their chase can be quantified as follows. As the number of cycle increases from the initial stage to the most extreme numbers, humpback whales engage in a coordinated effort to encircle the prey. During this process, they dynamically adjust their position and tactics to maximize their efficiency in chasing and capturing the prey. The surrounding the prey and winding refreshing of the prey has been finished during the investigation period of whale advancement calculations. Set the maximum number of iterations, design variables, and population system to zero. Determine the fitness function for every search agent for every design variable. And then select the optimal solution or the greatest fit and have the other search agents attempt to adjust their position to match it, which are all executed in the whale optimization algorithm, which is shown in figure 5. While coming to the results and discussion section, the effectiveness of the PWM rectifier employing the newly suggested controller is evaluated across the four distinct operations, considering the metrics like rise time, settling time, and the power factor. The different operating conditions are given in below. Under condition 1, figure 6 depicts the output voltage waveform of a DC side observed during the simulation. It illustrates that the DC side voltage can reach the steady state value in 0.058 seconds and remain stable when the output voltage of the derived double closed loop control system is set at 800 volts at 0.25 seconds. When the load resistance value undergoes a change, the output voltage is affected, but it adjusts to the desired value within 0.05 seconds. While coming to the figure 7 depicts the observation of voltage and current waveforms on the grid side at 0.25 seconds. The load resistance suddenly halved, causing an increase in current amplitude, where the voltage and the current on the grid side consistently remained in phase, indicating the maintenance of unity power factor. As a result of this, there is only a slight pollution on the grid side. While coming to the condition 2, figure 8 illustrates the behavior of the system under step changing input side. When the rectifier is in a steady state condition, the unbalanced state in AC supply happens between t is equals to 0.4 to t is equals to 0.6 seconds. The results shows that the DC link voltage varies around its reference value in both controller scenarios. Next, coming to the condition 3, the figure 9 depicts the simulation results of unbalanced AC supply and unbalanced AC supply condition. It is clear from the image that when there is a sudden changes from input side, there is a two changes at 0.39 and a large changes from 0.55 to 0.65. Hence concluded that supply change leads to different variations. While coming to the condition 4, this case study investigates the effects of load changes on the DC side of the rectifier. It examines the impact of reducing the load by 50%, which is reflected in the figure 10. And the table shows the performance of the controller under various conditions in terms of rise time, settling time, and the power factor. While coming to the implementation results, the validation of the simulation study occurs through examination on a three-phase active rectifiers laboratory setup. In the initial investigation, it is assessed to the proposed methods, steady state performance, experimental outcomes under various DC voltage set points are depicted in figure 11. In figure 12, the examination is done at the two voltage set points, that is 715 volts and 800 volts are tested. The results indicated that at maximum instantaneous error is very less, and consequently it is it is reduced. Hence, it is concluded that the proposed method yields a steady state error which is closer to zero. And from the figure 13, we can see that the voltage ripple during the full load operation. As a result, in the worst situation, that is full load operation, the voltage ripple is less than 3%, demonstrating the enhanced effectiveness of the controlled strategy. Next, moving on to the conclusion part. The proposed control strategy exhibits a rapid startup and excellent dynamic performance, promptly readjusting to a specified value upon load fluctuations. It effectively shapes the network side current into a sinusoidal waveform, mitigating the harmonic pollution and maintaining unity power factor operation. And also, from this method, which offers a superior operability and flexibility compared to the traditional techniques. And it aims to expand the effective voltage control range of a three-phase PWM rectifier and by enhancing their dynamic and static performance for practical application. These are the some of the conclusions which I have obtained for my article. Next, these are the some of the references which I have considered for the article. And finally, thank you.